Okay, so quick recap from yesterday. Uh, we were talking about paging, okay, memory management scheme that allows you to get rid of external fragmentation. And the basic idea is you take a process, process is not shown here, you take a process, you partition it into fixed size chunks called frames or other pages. Pages are assigned to the same fixed size chunks in RAM called frames. Okay? And you will relax the restriction that the process has to be resident contiguously. A page can be resident anywhere there is a free page frame. As a result, there is no external fragmentation anymore. Okay, you can grow and shrink the process because shrinking is just you deallocate some frames, the pages, the frames become free. Allocating new pages is just if you add some entries to the page table, allocate some more memory, map the page to that frame. Okay, so you can grow and shrink processes, you can share processes. What becomes more complicated is the translation from virtual to physical addresses. You need this data structure called page table, which keeps track of where each page for a process is resident in memory. It's a table that maps page I is in which frame. Okay, so the way you do the translation is take a virtual address. The high order bits is the page number, low order bits are the offset. You take the page number, offset in, rather index into the page table. That's ith or the pth entry that tells you the page frame, and you simply plug that into the address. So the address that you're looking for is this frame in main memory and that offset within that frame. And that's how address translation is going to work. We talked about storing the page table in registers versus memory. We said memory is better because there's no size restriction, but it's slower. So we will speed up accesses to the page table using the TLB, translation look aside buffer. That's really a recap of last time. Are there any questions on this? We are going to continue that discussion and talk about 2 or 3 different schemes that come out directly from this discussion yesterday. Any questions on paging? Okay, half the class has gone missing. More than half, a good 2/3 of the class is missing. Okay, so today we will talk about a new scheme called segmentation. We'll start with the motivation for it and then we'll see what it is, what does it do for us. And then after segmentation, we'll look at 2 more techniques, okay, that derive from segmentation. Okay. Now, if you look at paging or anything we have talked about so far as memory management is concerned, we said a process is a linear array of bytes. Okay. We said process as n bytes and you address it from 0 through n minus 1. We also said in paging that pages are rather a process is partitioned into chunks, fixed size chunks called pages. They're mapped onto frames. Okay. Now this is the hardware view and the OS view of the process. Okay. This is how OS views a process. It doesn't care what's inside a process. The process is simply an address space with n bytes in it. Okay. This is how the OS views it. Okay. Now the compiler's view of the process is very different. Okay, when a compiler compiles the process, it assumes that the process has segments. Okay, we talked about this. I showed you this picture maybe in lecture 3 or lecture 4. We said there is a code segment. What are other segments? The process. Code segment is where you put the source code that's compiled to machine code. 2 more. Stack and heap. Okay, so these are the 2 data segments, that's the code segment. Okay, so this is how a compiler views a process. It says code goes here. If you want to allocate variables that are local, you put them in the stack. If you want to allocate variables or data structures that are allocated on the fly, you put them in the heap. This is how a compiler is going to view a process. Now this view is not going to map directly onto a view of paging, which is I don't care what's in there, I just take the memory and chop it up into pages. That's how the OS views the process. Okay, so now we are going to take a step back and says if the compiler views each process as having some number of segments and each segment has a purpose, which is a code segment or a data segment, okay, then can we do some memory management scheme that directly map onto this view as opposed to a paging? Okay, that's basically a memory management scheme called segmentation. Okay, the reason this is important is when I said last time that the compiler generates addresses that are relative to the start of a process, that was sort of true, not quite. What the compiler actually does is that it creates this notion of a segment within the address space, and it generates offset with respect to the segment, not with respect to the process. So it says, you could say if you have a, let's say, code segment and you have a for loop and there is a jump, then you will say go jump to this offset with respect to the start of the code segment. That's what you're going to say. Or if you put a variable in the heap, you will say this variable or integer I is the 100th byte of the heap segment. This is how the compiler will generate addresses, not with respect to the actual start of the entire process itself, it's with respect to the start of the segment. Okay? So given that fact, the question is how are we going to design a memory management scheme that takes segments into account. Okay? So this technique is referred to as segmentation. Okay? So in this scheme, we will assume that a process has some number of segments as opposed to some number of pages. Now it has some number of segments. Segments are assumed to be of arbitrary size. There are no size restrictions. Okay? And the way we are actually going to generate addresses is you number the segments that are in the process, and you simply say when you generate an address, I want the ith segment and this offset within the segment. So the source segment or a code segment is segment 0, you'll say segment 0 10th byte. Or if you are trying to access the heap, this is 0, 1, 2, you'll say segment 2 50th byte. Okay, so this is how you are going to generate addresses. Okay, segment number and an offset within the segment. And segments are numbered. Okay, and now what you do is what we did in dynamic relocation, but a generalization. For every segment, there is a base register and a limit register. Okay, the base register is the start of the segment, and the limit register tells you what is the size of the segment. Okay. So you are simply going to say if you want the ith segment, you go and access the ith entry and say where is this segment in memory. Okay, this base register is the starting address of that segment in main memory. Okay, so you will look at the start address in main memory, and then you will go look at the offset and access the right address you are looking for. Right? So in other words, memory is allocated in chunks of segments rather than pages. So we don't require the process to be contiguous, but we are requiring that each segment be contiguous. So if this is the view of the process, and let's say this is main memory, so you can map this heap segment here. Okay. The stack can be put here, and the code can go somewhere else. Okay. Each of this is contiguous, but they don't all require you to be contiguous together. Okay. So now the base, if that's the heap, then this is the base register of the heap will point to that address there. Okay. That's what will be stored here. So if you want the ith byte, you will look at this address and then access I bytes down. Okay. So you have a collection of base and limits. So this data structure is now referred to as a segment table. Just as we had a page table, you have a segment table and you just access it, look at the base address, and you do the same logic we had for dynamic relocation, take the offset and this address, add them together, you get a physical address. Is that clear? Yes? Okay. So if that is the case, so you need hardware support for this scheme, which is multiple base and limit registers. Okay, so this requires you to have registers, which are segment registers that are going to store the start address of each segment. Okay, and so clearly we said registers are fast. Okay, so we can access the register base address and generate the physical address with a good efficiency. Okay. And now since the number of segments is somewhat limited, so the number of pages could be very large, so you couldn't store the entire page table in registers. But the number of segments is not that many. Okay, you may have, in this case, only 3, but you may have maybe 10 segments. So you need not a whole lot of registers. So it's okay to put the segment table in registers rather than storing it in main memory. Okay, it's much faster. Okay, so efficiency is not a problem here. Unlike in page table, we had to put the page table in memory because it was large and we had to put a cache, which was the TLB, to speed it up. None of that is necessary. Now that said, there are still problems with this approach. Okay, what is the main drawback of using segmentation?
This bigger
They are bigger chunks. Yes, what was the point you were saying? This could be of arbitrary size each, because you don't put a restriction on how large the code is or how large the stack is or anything like that. Any ideas on what might be a disadvantage? We have already looked at the disadvantages of various schemes. Some of them apply here as well. Okay, so if the chunk is of arbitrary size and you are allocating entire chunks, what might happen in memory? Yes. Okay, so the main problem is if you are always allocating variable size chunks, you are going to have the same problem we had in contiguous allocation, because each of these chunks are of different sizes. There will be multiple processes, so you will be left with arbitrary size holes. Yeah, now your fragmentation is back. Okay, you are going to have external fragmentation. Okay, so this is a compiler's view of the process of what a process looks like. Okay, it maps nicely with what the compiler is trying to do. Okay, but because we are allocating fixed size not fixed but variable size chunks, and putting them in one location in RAM, you are going to be suffering from external fragmentation again. Okay, is that clear? Okay, so we are back with external fragmentation. So what do we do? So we like segmentation because it's the compiler's view of a process. That's how the compiler views a process. Saying let's fetch an instruction from the code segment. Let's fetch some variable from the data or a stack segment. This is how it is actually generating code. But because you now allocated those entire segments in contiguous locations, we are going to suffer from external fragmentation. So what could we do about this? Not that hard. Go ahead.
Either defragmented or not stored contiguously.
Okay, defragment or not store it. You have something to add?
Can you implement paging inside segmentation?
Can you what?
Implement paging inside segmentation.
Okay, implement paging inside segment. So all of these are clearly things you can do. If you have fragmentation and you want to allocate big chunks, you defragment. Expensive. Okay, but you can do that. Okay? Second point that was made was don't store it contiguously. Okay? Keep in mind that the segments themselves are not stored contiguously anyway. Okay? Each segment is stored by itself. So these three segments are stored, as you can see, in three different locations. But the point is each of these segments are still stored contiguously. Okay? So you want to take this one step further and say don't even store the segment itself contiguously. Forget independent segments. And the way you will do it is you will essentially treat each segment like a process. You'll say this is an arbitrary size piece of memory. So the right way for me to allocate it is not a large chunk. I'm going to chop this up into smaller pages and allocate pages. Okay? So you are going to essentially page your segments. Okay, so that's combining segmentation and paging. Here's a picture that shows you exactly that. So this is referred to as segmented paging. Okay? So in the earlier case, we has treated a process as having an arbitrary size and we chopped it up into smaller chunks. Here, a process has segments. Each segment could be of arbitrary size. That's a heap segment, a code segment, a shared library segment. They tend to be many of the segments that are associated with a process. Okay. So now what we have done is each of this can be of arbitrary size. So you say I'm going to actually partition this into fixed size chunks. Treat this exactly the way we treated variable size processes. Now we treat variable size segments as being paged, and each of these fixed size pages is mapped onto main memory. Main memory still has a sort of a sequence of page frames that are of fixed size, like 4 kilobyte or 8 kilobyte pages. Now what is stored is a page from a segment. Okay, yes?
What advantage does this show over just paging?
Okay. Question is, what advantage does this give you over paging? Why could we not treat the entire process as a collection of bytes and just get away with it? Right? That's a very good question. So what we are trying to do is to retain the compiler's view of a process and the OS's view of a process. The OS likes a paged view. because it likes the convenience of allocating memory in fixed size chunks. Okay? Compiler couldn't care less. Compiler is actually, when it's generating memory addresses and so on, it is saying go to the code segment, the 5th byte, fetch that instruction executed, or go to the heap segment, your array is stored starting at this offset. This is how it is generating addresses. So we want to combine the two views. We don't want the compiler to be forced to doing what the OS wants it to do, which is don't worry about segment, just treat this as a simple linear sequence of bytes and just index them. Okay? That's what the OS is trying to do here when you pay. So we are trying to merge the two. Okay? We want the compiler to continue to do what it does, but we want the OS to adapt to it. Okay? So we say, let the compiler treat the process as a collection of segments. Let the segments be of arbitrary size. Okay? So now, if that is the case, rather than paging the entire process, we'll just simply page each part of that process, and we still get the same benefits as we got when we paged the entire process, which is there's no fragmentation. Okay, this is going to complicate that address translation logic. Okay? So in doing this, we have tried to retain the best of both worlds again. This is where all these trade-offs come in, but we don't get this for free. We are going to make some things more complicated. Okay, so rather than reading this out, this is best shown with this picture. So now what we have is we have two data structures, not one. We have a segment table that tells you where each segment, or we have a segment table and we have a page table for each segment. Okay, earlier we had a page table for the entire process. Now if you have 10 segments, you are going to have 10 page tables. You treat each segment as if it was like a little process. Okay? So what we have is now your address has 3 parts. Okay? You say go to segment S, go to the pth page of that segment, and D is the offset within the page. Okay, so the way you generate an address is you say this is the segment, this is the ith page in the segment, this is the offset within the page. 3 components. Okay. And what you will do is you will look at the segment number, you look at the segment table. Now the segment table earlier in segmentation pointed to where the segment was stored in memory. Now it is a pointer to the page table for the segment. Okay. So this thing is actually pointing to a page table. Okay. So it's a 2-dimensional, 2-level structure. Look at the segment table and say where is the page table. So the segment table is simply pointing to the page table. Then you basically say I want the pth page. So you basically go and say where is the pth page stored in memory. That gives you a frame number. You take the frame number and the offset, that gives you a real address. Okay. 2-level lookup. In pure paging, it was simply 1 level. You only had this. In pure segmentation also was 1 level. You only had this. Segmented paging, you need to have both. This is how you are retaining the compiler's view. We still pretend as if the process was a collection of segments, but each segment is paged, so you need a page table for every segment. Okay, this is how we are going to combine it, try to achieve the best of all worlds. Clear? Okay. So now, if that is the case, you think of this as an OS design question. You are OS designer. You are this more complicated memory management scheme. It's called segmented paging. It requires multiple data structures. Okay. Segment table, page table. Where do you store them? For efficiency reasons. Okay, so we have our usual choices or usual suspects, or you put them in registers, you put them in main memory. So what would you store, where, and why? Yes. Okay, so registers are not good enough because there are only a few of them. You cannot actually store a large number of entries in registers. Okay, good point. So you cannot store this all in registers. That's a valid point. Yes.
I think you could store the segment table in the registries because there's only 3 entries per process, and then each one has a page table, so you need to put those in there.
Okay. Second suggestion being made is treat them differently. Okay. Don't treat them as if I store both of these in registers or both of this in memory. There are only a few segment entries. In this case, there are only 3: code segment, stack segment, heap segment. Okay. You can find 3 registers on a machine, put them in this register. So that's very fast access. Okay. So we are now making use of how large each of these tables are. If this is a small table, the best place to put it is in register. That's the fastest memory we have. You cannot get any faster access than putting things in register. So segment table goes in registers. Okay? Page tables are of arbitrary size. It depends on how large the segment is. Okay? You may write a lot of code and create a gigantic code segment, or you may allocate a very large array and create a gigantic heap segment. Okay? So these could be of arbitrary sizes. You cannot put so many entries in registers. Okay? Same as what we did in paging, we are going to stick this in main memory. Okay? Now, as soon as you put this in main memory, you have impacted performance. Main memory is the slowest in the hierarchy. Registers are the fastest. Okay? So every time you access a page table, you are going to basically do a memory lookup, and then you are going to access the actual physical address. Okay? So every memory access becomes 2 memory accesses. Your factor of 2 slow down. Okay, so what will we do? Okay, you will cache the addresses, and no different from what we did yesterday. Okay, so I don't know if I have a picture. No, I don't have a picture. So what you will do is you will simply stick a TLB. The same thing we did for paging. We'll also bring a TLB. A TLB is a fast cache for the page table. So the page table goes in main memory. Okay, and we said the 90-10 rule applies to processes. That has not changed. 90% of the time, a process is only touching 10% of its memory. That's the part of memory it's working on. That's where the current data or instructions are stored. So you only need to store a few of these page table entries in a faster cache to speed things up. So you throw in a cache, you speed things up. Okay? Every time there's a cache miss, you will pay the price of 2 memory accesses. But then you'll fetch the page table entry and stick it into the cache. So any subsequent accesses to that page are now sped up because the page table entry is in the TLB. So you don't need to pay that price. Okay? So this is our sort of a grand unified scheme where we are trying to sort of not make the compiler do things it doesn't want to do, nor make the OS work hard to defragment or anything like that. So we are trying to combine all of these ideas into one. So segment table goes in registers, page table goes in main memory is slow, so we put a TLB. So what we will do is we'll first access the segment number, okay, that will give you a pointer. So that's the base register will give you a pointer to the page table. Okay. Now you basically then say for that page table, okay, where do you have an entry corresponding to the pth page in the TLB? If so, you are done. Okay, you just look up that entry and that gives you the frame number. If that pth entry of that page table is not in the TLB, you will actually go to the main memory, fetch that entry, put it in the TLB, and resolve that address. Okay. So either way you will resolve it. One is a fast path, the other is a slow path. The TLB miss is the slow path. Okay. So this is how we are going to do memory translation. You, meaning the hardware, will do this for you, but this is what we have to put in place. Okay. Again, all of this is transparent to a process. Okay. The process is simply generating addresses, and all this is happening internally. Okay. So the process never sees this. Even the OS doesn't actually see it. It knows about page tables and so on, but it is not involved in doing the translation. It lets hardware do all of these things. Okay, so you still need an adder there to generate addresses and so on. Okay, is that clear? Okay, quick exercise to see whether we can now wrap our brain around all of these data structures. So it's a similar example as yesterday. Okay, we'll assume main memory has 256 bytes or addressable words, but let's assume each word is a byte for simplicity. Okay. Page table, okay, can index up to 8 pages. Each segment, or rather, is allowed to have 8 pages. That's the maximum size of a segment. Page is 32 words. Okay. And we assume that a process can have at most 8 segments. It can have at most 8 pages per segment. It can have at most 8 segments. Okay, that's the scenario given to you. Okay, these are questions we need to now answer keeping this picture in mind. Okay, that's the picture in mind. So first question is, how many bits do you need for a physical address? What's the range of a physical address? Yes. 0 to 255. We said memory size is 256 addressable words. That means addresses will go from 0 to 255. That's the range of the address. So how many bits do you need? 8 bits. 255, 8 bits. Okay, so physical addresses are 8 bits. Okay. Now we'll ask a more interesting question. How many bits do you need for a virtual address? Okay. Until now, in all of the schemes, the length of the virtual address and length of the physical address was the same. Right? For segmented paging, it's not going to be the same anymore. Okay, we'll construct the virtual address and you'll see how many bits for the virtual address. Okay. To understand that, we should simply ask how many bits do you need for the segment number, page number, and the offset part. Okay, so how many bits is this is what we are going to ask. Okay. The main memory is simply page number and an offset, so you need some additional bits to hold the segment number. Okay, this is why the virtual address is actually going to be bigger or longer than a physical address. Okay. So how many bits do you need for the segment numbers? And what's the range of segments, segment numbers? 0 to 7. So whenever I say what's the range, you should ask how many segments are there. That's the number of segments you are going to address. Okay, so we have 8 segments. If you have a process with maximum of 8 segments, you have the addresses have to go from 0 through 7. Okay, so that's 3 bits. Okay, so 3 bits. So segment numbers are 3 bits long. Okay, they go from 0 through 7, or 8 segments. Page numbers, how many bits? Yeah, how many pages do we have? 8 pages per segment. Again, page numbers within each segment. Each page table can have 8 entries. If there are 8 pages, so that's 3 bits again, 0 through 7. Okay. And then offset within a page. What are the address range for an offset within each page? Should be a little faster if it's an exam question. Yes. 0 to 31. All of the answers are right there. Still just need to read. So page size 32 words. Okay. Page offsets go from 0 to 31. So there are 32 addressable words. That's 5 bits. Okay. So 5 bits for the offset, 3 bits for the page number, 3 bits for the segment. 11 bits. Okay. Virtual address is 11 bits long. Physical address is 8 bits long. Okay, is that clear? That's basically, so this is 3 bits, this is 3 bits, that's 5 bits. Okay, so basically the segment number is discarded for a physical address. You only need a frame number and an offset within the frame because main memory is simply a collection of frames. At that point, we ignore the segment completely. That's only a compiler's view. We just used it to actually index into the right page table. That's all we did. Okay, is that clear? So we already answered all of these things, segment entries and page tables and so on. Anything I should clarify here before we move on? Okay, we talked about efficiency, where do you store each data structure. We talked about how address translation works and why we have segmented paging at all. Okay, last point is sharing. Okay, yesterday I said when we had paging towards the very end of the class, I said if you are paging, you can share pages. Okay, how do you share pages? Yes.
2 different page tables. Specific pages are put into the same frame.
Okay, that's right. So the way you are going to share pages is if you have a page, you want to share it across 2 processes, they will have 2 page tables, they will both point to the same page. Okay, this is how we are going to share pages. Okay. Now it should be clear that you can also do this at a segment level. You can also share entire segments. Okay. And the reason this is useful is because I said in this picture I showed you that certain segments are shared libraries. Okay, this is a good segment to share. If you want to load the C library or you want to load libraries that are related to your Java virtual machine, you load it only once. There may be 10 processes that are all requiring that library. Okay? We can just share it. You don't need to load it into each process. Okay, so we are now going to share entire segments. Okay, how do you share segments? First thing is, of course, you can take all the pages of that shared library and have pointers going to the same pages, just as we did for paging. Okay, but there's a smarter way to do this. You can essentially just share the page table. Okay. So let's say there are two processes. They have both segment tables. Okay. Both of the segment tables can point to the same page table. Clearly, the page table itself is pointing to the pages of that shared library. Okay. So rather than having the two page tables point to the same frame, since you're sharing the entire segment, you can simply take the page table and the segment table point to the same page table, and you're done. Okay, because then when you want to say C library or Java library, you basically go to the shared page table and then point to all the pages that you loaded. You are done. Okay. Now this also allows you that if you don't want to share segments, but you want to only share, let's say, certain pages of the segment, you can still do that. In that case, you have independent page tables, but those page tables will point to maybe one frame that is shared. Right? That flexibility is still there. If you want to do shared memory or do shared buffers of some sort, which are not shared libraries, so they're not entire segments, but smaller regions of memory, that is still possible. So you can share at the page level or you can share at the segment level. Okay, so sharing of segments, as you can imagine, is very common. Okay, so your OS is smart enough that to understand that there are many processes that all use the same set of libraries. So it doesn't repeatedly load the libraries again and again. It only loads it once. Okay. The code segment may be different. That's the code for that application, but the code may require you to use lots of other libraries. Okay. Those are only loaded once and shared at the segment level. Okay. We still have TLBs. I talked about implementation already. Okay. Registers. That's where segment tables are stored. Page tables in memory with the TLB. Okay, so quick advantages and disadvantages. So I talked about several advantages already. So you can support much more flexible levels of sharing. Okay, processes can grow and shrink. Okay, in this case, let's say heap can grow and shrink independently of other segments in this case, or the stack can grow and shrink. The code segment typically doesn't grow. You just load the code and it's just set. Okay, so you can accommodate growing and shrinking processes. There is no fragmentation, okay, and so on. Okay. The disadvantage is your address translation is still going to be somewhat slower, okay, because there are two lookups to do. Okay. First, you will look up a segment table, then you look up the page table. Okay. Yes, we have made it efficient as possible by storing the segment table in registers and caching the TLB entries. But nevertheless, there are two lookups to perform. This is something that we have to realize. So there is going to be a price, which is address translation is slower. Context switches are also going to slow down, okay, because now there is even more state to store and restore. Okay, because you have to, when you switch from one process to another, okay, you will have to take all the page tables for the process that's being evicted, store it in the process control block, take the segment table, store it into the process control block. So there's multiple page tables and a segment table per process that has to be stored and restored. Okay. More work to do. So context switches will slow down. Address translation will slow down. Some, okay, not a whole lot. So those are some pros and cons. Okay. So last point here is fragmentation. Okay. So we said segmented paging has no external fragmentation, but it does have internal fragmentation, like we had in paging. The question is, how much internal fragmentation do we have in segmented paging? Okay, before we answer that, let's try to recollect what was the level of internal fragmentation in a paging scheme, pure paging scheme. Anyone remember? Yes.
On average, half the size of a frame per process.
Okay. Half the size of a page or frame per process. We said that you cannot force a process to be an integral of the page size or a multiple of the page size. It will be of arbitrary size. So there will be some wastage in the last page because you allocate memory in granularity of a page. So there will be some waste in the very last page of the process, and on an average it will be half a page. Sometimes it will be more, sometimes less, but on an average half a page is wasted per process in pure paging. Okay. What about segmented page?
Scale by the number of segments.
Scaled by the number of segments. You will essentially again have the same problem. You cannot force segments to be some multiple of the page size. Segments are of arbitrary size. So the last page of every segment is going to see some waste. Okay. So basically you will see half a page per segment being wasted. Here it's half a page per process. Okay. In other words, this is half a page per segment times the number of segments. But it's just easier to say half a page per segment. Okay, so there will be little more internal fragmentation in segmented paging. Okay, no external fragmentation. So internal fragmentation we'll live with. Okay, if you waste 2 kilobytes of memory and you're 2 gig, don't really mind. Okay, there's not a lot of waste to go after. Okay, so last data structure I'm going to talk about is what is referred to as inverted page tables. Okay, so when we have very large, so this is useful when you have extremely large processes. Okay, so you must have heard of 64-bit architectures. Okay, and we have said in 64-bit machines you can have very large RAM sizes. Okay, you can have a machine with a terabyte of RAM, not disk, I'm talking about RAM. That's how much you can address. Okay, so process sizes are also allowed to be very large. So you can have, because you have 64-bit addressing, you can create very large processes. Okay. Now, just because the process is very large or can be very large doesn't mean that every process is going to be that large. Most processes are going to be of usual sizes that we see. Some are tens or hundreds of megabytes. But your addressing will allow you to store very large processes. So that brings about the question of how large should the page table be when the new process is allocated. Let's say you start a new process. On a 64-bit machine, this process could be potentially up to a terabyte inside because that's how large the process is allowed to be. So then you say, how large should the page table be? Okay, how large a page table should I allocate? Okay, you could say I will allocate a page table that assumes the worst case as large as the entire process could potentially be. You create a very large array and you store it in main memory. And maybe the process doesn't turn out to be very large and it only uses maybe 10% of the entries and the rest are all wasted. So you allocated a gigantic array and wasted all of the space. Okay. So what frequently happens when you have these higher bit architectures is you have what are called sparse page tables. You have page tables where only some of the potential entries are actually in use and there are a lot of entries that are not used at all. So pre-allocating very large data structures is of no point because you're going to waste a lot of memory because this page table has to be stored in kernel address space. Okay. So you don't want to create some gigantic array and then have it go waste. So you want more efficient data structures that will allow your process to grow to as large as it needs to be. And yet, if the process is not very large, you don't want to waste some needless space allocating gigantic page tables. Okay, so the data structures that are used for such in such scenarios are referred to as inverted page tables. Okay. An inverted page table is simply a hash table. I presume you know what hash tables are, right? Hashing 230, maybe 187. I don't remember when you learned hashing. So essentially, rather than storing the page table as an array, which is what we've assumed so far, you will store the page table as a hash table. Okay? You're simply going to hash. So remember, what is a page table? It's basically you index into the page number and gives you a frame number. Okay? So you will hash with the page number or the page number, and then the hash table will simply give you the frame number for the page. Okay? So rather than creating an array, you create a hash table and you insert entries. And then you simply index into the hash table and you extract those entries. And the hash table, the data structure we assume is sophisticated enough that it can grow and shrink dynamically. Okay. You could have potentially allocated arrays that also grow and shrink, but that's a little more complicated. because the way arrays are constructed are they're contiguous, stored contiguously. This is how arrays work. So if you, rather than doing that, you basically construct a data structure that's designed to grow and shrink. It doesn't, a hash table never pre-assumes that it will have only 10 entries or 15 entries. That's what an array does. You basically, array is a trivial hash table where the index is letting you index into the value of the hash table. Okay, so it's a pre-allocated hash table. A real hash table is dynamic, it grows and shrinks. Okay. So more sophisticated OSs have started using inverted page tables. An inverted page table is simply a hash table. It's referred to as an inverted index. Okay. So this is how you can make your page table more efficient and not have it waste space. And yet, as the process keeps growing, the page table, or in this case, your hash table, grows with the process. Right. Keep this in mind, what an inverted index is, because you are going to see it very soon in lab 2. Not in the context of paging, but there is something you have to do about inverted indices in lab 2. Okay, is that clear? Inverted index, simply a hash table, and page tables are stored as hash tables rather than arrays. Okay, nothing else has changed. You still have a TLB, you still have the page table in memory, and so on. We simply change the data structure used to store page table entries from an array to an index hash table. Okay, so we are going to move on to the next scheme, but since we are done 4, of which 2 we just covered, I'm going to very quickly recap. So we started with relocation, which is contiguous allocation. It simply requires base and limit registers, somewhat simple, but not very flexible, results in external fragmentation and so on. The second, this is not in the order we looked at, but this is just the 4 we covered. Another memory management scheme is segmentation. This is the compiler's view of what a process is. Okay? So we chop up the process into arbitrary sized segments, and each segment is now stored contiguously. Okay? So we have not gotten rid of external fragmentation, but we are now able to allocate each segment to an independent location. Okay? But each segment has to be contiguous, but 2 segments can be in 2 different regions of memory, but you still have external fragmentation. This allows you to handle the compiler's view of the process. Okay? Paging is the OS's view of the process, which basically says to get rid of external fragmentation, you cannot do variable size allocation of RAM. You have to do fixed size allocation. So you partition your memory into frames and then partition the process into pages and map frames to process, pages to frames. Okay. And then we combine segmentation and paging. That's what we just did today, which combines the OS's view and the compiler's view of the process. Okay, this is clearly the more complicated approach because you need multiple data structures, segmentation and segment tables and page tables for each segment. Okay, so that's a summary of what we have talked about. Okay, now those are 4 different schemes, and the thing to keep in mind is in all of those 4 schemes, we have still implicitly assumed that the entire process is actually resident in RAM. Okay, so we said the whole process is actually stored in RAM. Now we are going to relax that assumption. Okay, so not only will we let a process not to be resident in RAM, we allow a single process to be bigger than RAM. Okay, so we are now going to let the aggregate of all the processes will clearly be bigger than the amount of RAM you have, more than RAM. But we can let start processes where the process itself is larger than the size of main memory. Let's say you have 2 GB or 4 GB of RAM on your machine, you can start an 8 GB process and we'll still be able to run it. Okay, the reason we can run it is we don't require the entire process to be in main memory at the same time. Only parts of the process can reside in main memory. Okay, so we are going to essentially talk about this scheme. This is referred to as demand paging. Okay, so what we are now going to do, the way we are going to implement this is as follows. We are going to use disk as a backup region for RAM. Okay, think of it, disk as a much larger but slower portion of main memory. Okay, disk is the backup. Okay, and what we are going to use is just as a TLB was a cache for main memory is now going to become a cache for disk. By default, when you start a process, we are going to store that entire process on disk. And we are going to cache in parts of the process into main memory as and when needed from disk, and cache out portions you don't need. Okay? This allows you to give the illusion of essentially infinite RAM on your machine. So the disk is very large. You may have 200 GB of disk or a terabyte disk on a PC. Okay? Main memory may still be a few gigabytes or maybe 10 gigabytes, tens of gigabytes. Okay? So since disk is much larger, we will essentially give an illusion that there are no memory restrictions. You can start as many processes as you want. Okay? It's not going to be limited by how much RAM you have. Things may slow down as you have more processes because more stuff is on disk and has to be brought in or pulled out. But you will not be told you used up your 4 GB, so that's it, and nothing can be done about it. Okay. This scheme is referred to as demand paging. Okay. Most general purpose operating systems already have demand paging built in. This is not true for specialized operating systems. For instance, in phone-based operating systems like iOS or Android, there isn't demand paging built in yet. Okay, in many other approaches. So if you actually try to start too many applications, okay, you are not given an error that your process is actually not going to fit, but internally what the OS is doing is actually killing processes. But it saves the state of the process before killing it. So when you try to switch to that process, it just resumes that state. So it looks like nothing actually happened. But it is effectively ejecting processes because it cannot store them in RAM. On general purpose operating systems, you don't do that. You actually simply put it out on disk and bring it back when you need it. And so the illusion of an infinite memory allows processes to be larger than RAM, a process to execute even if not all of it is in RAM, and allows more processes than you could potentially fit. Okay, so again, if you can go and take a look at what's happening on any given machine, you will see this happening. Okay, so you can see this. So these are actually processes on this machine. This is the amount of main memory that has been allocated to. That's the actual size of each process. Okay, you will see this process here has 6 megabytes allocated in RAM, but that process is 200 megabytes in size. So rest of it is actually on disk. Okay? If you simply sum this up, so this machine has 4 GB. If you simply sum it up, you will see that it is much bigger than 4 GB. So the total size of all the processes is much bigger. Okay? And you'll see that what is in RAM is only a small subset of what's actually the size of the process. So that's the size that is actually resident. And you can fetch portions of the process into RAM as and when needed. Okay, yes, question. How do you determine where to store it? So we are still going to use paging. Okay? Except that the page table will now tell you whether the page is on disk or in main. Okay, so we'll generalize what a page table will do for us. It will essentially point to one of the two. Okay, so that's basically what demand paging does. Now let's look at this in a little more detail. So think of demand paging as using a memory as a cache for disk. Okay? Page table is a memory map, indicates whether the page is on disk or memory. Can you bring the page into memory as and when needed? Okay? So the reason this is going to work for us is the 90-10 rule. Okay? So basically that says that 90% of the time the process works on 10% of its memory. So those are the 10% of pages you have to have in disk. Otherwise your performance is going to be terrible. Because now memory access may become not two memory accesses but a disk access. If you try to address a memory page and the page just happens to be on disk, now your instructions are executing at speed of disk. Several orders of magnitude slower. Okay, I can tell you that performance will be so bad you will not want to use your machine. Okay, this will happen if you get overcommitted. So you want to ensure that there are very, very few instructions that will actually access a memory page that happens to be on disk. If that happens, you get what is called a page fault. Okay, this is like a miss. So you have to go and fetch the page. So the number of page faults have to be as little as possible. Otherwise your performance is going to be poor. Luckily for us, because of the 90-10 rule, okay, we can get away by keeping only a small portion of the pages in disk. Okay? That's referred to as the working set. The working set will change over time as the process executes a different part of the of its code. Okay, but at that point, we'll fetch in the new working set. There will be a few page faults. We'll fetch in the new working set, and from then on, things will be fine again. Okay, so every once in a while, you'll pay the penalty of having to fetch pages from disk. But once they are there, the assumption is you'll continue to work on them, okay, for a little bit, so you will get good performance. Okay, so we are going to exploit this notion, which is called locality, which is that you will basically try to processes work on the same set of pages for a period of time before they switch to other pages. Okay, so this is our new data structure. Okay, this is your paged process. Okay, that's a page table. Okay, so page table is basically pointing to this is the logical view where each of the pages are stored. Is either in memory or on disk. Okay, so some pages of this process. So these are pages. Some of these pages are here, and some of those pages are there. And the page table is telling you where it is. Okay, so if you try to access this page, for instance, okay, you'll say, oh, it's on disk, so that's a page fault. So what then you will do is that will actually cause you to switch to the OS. That's going to trigger a trap, actually. So you'll go into the OS and tell the OS, go fetch that page. So OS will fetch the page and bring it into memory. It will update the page table. At that point, the OS can resume execution of the process. Because the process execution will stall because the page is not in memory. You have to first fetch the page and then access whatever instruction you are trying to access in that page. Okay, so this operation is referred to as page faults. Okay, page faults are going to be handled as traps within the OS. Okay, the process never knows that the page is on memory or page is on disk. Process is simply accessing or executing instructions. Okay, when you dereference or try to do the address translation, the page table will tell you whether the memory address you are trying to access resides on a page in memory or resides on a page in disk, and you have to act accordingly. If it's a page in memory, you're done. Nothing to worry about. If it's a page on disk, then you have to suspend execution, trigger a page fault, and whatnot. Okay. Keep in mind that memory accesses are in the order of nanoseconds or microseconds. Disk accesses are in the order of milliseconds. Typical disk access takes 1 to 10 milliseconds. Okay. 1,000 times slower, 3 orders of magnitude or 4 orders of magnitude slower. Okay, so think of 1,000-fold slowdown in the execution of your process. Okay, that's a very significant slowdown. So you don't want too much paging to happen in your machine. Okay, but nevertheless, most of the time we can get away with it because of the because of the locality of references and the fact that you can keep a few of those pages in memory and you don't see much hit on performance. Okay. And what you get for a little bit of pain every once in a while is the assumption that now you are no longer restricted by the size of main memory. Okay. In fact, this process could have more pages than main memory. The rest of them will be actually stored on disk. Okay, we are relaxing a whole set of restrictions. You can have lots of processes. It looks like you have infinite RAM on your machine. You can keep starting as many processes as you want. The OS is not going to complain. You will start seeing slow degradation in your performance over time, but that's about it. Is that clear? Okay, so there are many questions about when pages are fetched and so on. Okay, so I explained a process where pages are fetched on demand. Okay, you access a page, it turns into a page fault, and then you bring the page. But there are other scenarios as well. Okay? You can load some pages when you start the process. Okay? You can load maybe the first 100 pages are loaded and ready to go. You don't wait for the page fault. Or you can start with an empty process, only bring its first page, code page in, start executing, and it will immediately start faulting and bring other pages. Okay, so you can do completely on demand, or you can prefetch some pages. You can even predict which pages might be accessed next and prefetch some pages. Okay, this also happens. This is referred to as pre-paging. If you predict what the process is going to access next and look at the instruction and the addresses and fetch those pages, by the time you actually execute those instructions, the pages are already been fetched. So there are no page faults when you are executing. You are fetching them in the background. Okay, so there are many different ways to optimize performance. You can prefetch You can predict and prefetch, or you can simply say, I'm going to do it on demand, and that's the way it is. Every time you fault, you're going to slow down your performance. And so these are all mechanisms you can put in place that determine when you are loading a page from disk to memory. Okay, so I talked about demand paging and pre-paging already. So page fault is the most important concept to keep in mind. This is an interrupt that occurs when an instruction refers a page that's not in memory. I said it causes a trap. Okay, the trap switches to the OS. The OS is told that the process is trying to access this page, go to disk and fetch it and bring it in memory and update the page tables. And until then, the process has to go and sit in the wait queue, waiting for its page to be fetched. Once it's done, then it's going to go back to the ready queue and resume execution. Okay, so process will give up the CPU when you have a page fault. Okay, keep that in mind. You cannot continue execution. So it's not just a slowdown, you have to stop executing or suspend executing until the page is fetched. Okay. Here's a quick implementation of our demand paging. So what we will do is we will basically have a valid bit for every page table entry. If the bit is set to 1, that means the page is in memory. The bit is set to 0, that says that the page is on disk. Okay, so first when you access a page table, you'll see is the bit 0 or 1. If it's 1, then you know it's in memory and you just look up the page table and it points you to the right region in memory. If it is 0, then you know that it's not in memory and you know that it's on disk and you're going to go fetch it from this. Okay? So this is how you are going to keep track. Okay, page table has one more entry now. That's a valid bit which tells is it memory or disk. Okay? And also the address of memory or disk is the other thing you store. Okay? So here is basically what you're going to do. So whenever the bit is not valid, you're going to select. So if you want to bring a page in, the other thing to keep in mind is if you bring a new page into memory, okay, this is going to be at the expense of some other page that you have to throw out of memory. It's not like you can keep bringing in pages. Eventually memory will fill up and you have to throw out a page. Okay, that's an important aspect of OS design which we are going to talk about also. It's called page replacement. The page replacement algorithm is going to say if you need to bring this page in, which page should you throw out? Okay, so you are first going to, whenever there's a page fault, you will run the page replacement. It will say go throw this page out. Okay, so you essentially invalidate its entry saying this page is now gone off to disk. You start loading the new page from memory. While that is done, you context switch to some other process, execute it. Some many processes get executed. Once you have brought the page in, when the disk I/O finishes, then the interrupt is done. Then you're going to update the page table entry and continue the faulting process. So this is all the steps you have to do. This is how you handle a page fault. This is what happens when the page fault trap occurs in the OS. This is all happening in the kernel. The most important decision, this part is straightforward. The most important decision is step 1. What are you going to evict? Okay, how do you decide what to evict, first of all? You can randomly pick and throw out a page, but sometimes that may be a bad decision. Is that clear? Now we'll talk about how to decide that in just a moment, but what you need to realize is the most crucial decision you will make is page replacement. You throw out the wrong pages and the process accesses them immediately, you'll get more page faults. Okay, so this decision has to be made carefully so as to minimize the number of page faults. You make this the wrong way, then you increase the number of page faults by throwing a page that was about to be used again. Okay, so last point before we talk about page replacement is this notion of swap space. Okay, you must have, if you know anything about Linux, you will know that Linux has swap partitions. Okay, and there are on Windows you have things called swap files. Okay, so what this is this is the space on disk where you keep the process. Okay, so I just said here, or this picture showed you that the pages of the process were stored on disk, but I didn't tell you where this is stored. Okay? So what you typically do is you create a special partition on your disk, and that is where you will store processes. The other partition is going to store files, actual files you create. but a part of the disk is reserved for storing pages of memory. So if you have a swap partition, as you may have sort of seen in Linux, that is a partition where the pages are stored and fetched. If you don't have a special swap partition, what the OS will do is it will create a large file on your regular disk drive, on your regular file system, and that's referred to as a swap file, and it is going to store pages and processes in that swap file. So if you accidentally delete that swap file, all your processes are going to terminate immediately. Okay, so never do that. Okay? Yes.
What's it called?
Swap file. Right. So swap files or swap partitions are where you are going to store your pages. Okay, you have files and now you have pages. Typically, OS manages swap files. You don't worry about it. Some part of your disk is just used to keep processes. Okay, and most of the time it's transparent to you. In fact, swap files are typically hidden, so you won't even see them. If you create a hidden file in your file system, so unless you know where to look, it will be all transparent to you. Okay, so that's your swap space. Now, the swap space really has to store the entire process, okay, because so by default we assume all pages are stored on disk, and a subset of those pages are brought in. Okay, so that means the code partition is on disk, the heap is on disk, and the stack is on disk. Every segment that you have is actually stored on disk, and you fetch it on demand. Now, there's one optimization you can do, which is the code partition is source code for your program or your process. Okay? So rather than loading it in memory and then putting it back on swap space, okay, it's already on the file system. That's the executable. Okay? So you can directly swap off the executable rather than creating an extra space and simply copying those pages, that data over. Okay? For the code segment and heap segment, you actually have to allocate pages in your swap space. Okay? For your source code, for your program, you have a choice. You can directly swap off the file that you started executing, because that's where all the code is stored. Okay. Or you can allocate some extra space and copy that file there and start swapping it. Either way, it's the same data. Okay. So what the OS will do is, as an optimization to save space, okay, it will actually, if you are executing a program, it will try to swap off the code that you have in the file of that program on disk rather than allocating additionals. What this also says is, if you have an executing process, okay, let's say you create some code, you create a binary and start executing it, and you delete that file while it's executing, again the process will crash. Okay, you can try this as an experiment. Create a copy of some executable. Okay, start executing it, double click and execute it, and then delete it. You'll see that the process will crash because you cannot swap off that disk anymore. Okay. Some OSs are smart. What they will do is, if you delete a process or delete a file for an executing process, it will actually remove it from the file system, but the underlying data is not removed. So it will convert that into a hidden file and still continue to swap off it. And then only when the process stops will it deallocate space. Okay. This is an optimization. Older operating systems, they'll simply crash saying you just killed the file. Now there's nothing I can do. Okay, so these are all things to keep in mind. So if you see weird behavior where at an executing process and you simply deleted the file or something, the process crashed, this is why. Because you're actively swapping off the code and you just remove the code. So if you have to have a page fault and to fetch new pages, the code that was on disk is now gone. Okay, so you can't swap off it anymore. So these are all things you need to do. So at any given time, any page of the process could be in the file system if it's a code page, it could be in RAM if it has been paged in, or it could be on swap space if it's not in RAM, it's swapped out. Okay, so these are both on disk and this is in main memory. Okay, so a page can be in any of these three locations at any given time. Okay, and clearly your page tables need to have extra information, valid bits and so on, that tell you, is the page in memory, is it on disk? If it's on disk, it could be here or here, depending on whether it's code or data. Okay, is that clear? So I'll do one more thing and then next time we'll talk about page replacement, and that's really the performance. We we have to be worried about performance, because the more paging you get, the worse your performance is going to be. Okay, so I will write this on board. Okay, so let us assume that you have a process running, and P is the probability it's going to see a page fault. That page fault essentially means it's accessing a page that is unfortunately on disk. Okay. So if you see a page fault, what is the speed of memory access? How fast is the instruction? How long will it take to execute this instruction if you have a page fault? Yes.
However long it takes to access to the disk.
However long it takes to access a disk. Effectively, the speed of this instruction is the speed of your disk. So memory access time is essentially disk access time. Okay. 1 minus P is the probability there is no page fault. Okay. When there is no page fault, memory access time is essentially whatever we showed for paging or all of those things. So in this case, I'm simply going to call it M. But this will be M plus TLB and things like that. But I'm just making it sort of simple just for discussion. Okay. So when there are no page faults, you access memory as if there is no other problem. Okay. This will be M plus TLB in the best case. When there's a page fault, you will essentially execute at the speed of this. Okay. Now what this is also saying is memory access time is 200 nanosecond. Page fault is 25 milliseconds. Okay, so this speed is 25 milliseconds. Okay. Memory accesses are 200 nanoseconds. Okay, look, this is 6 orders of magnitude difference. Okay, 6-fold, not 6-fold. 10 to the power 6 slow down if you actually have lots of page faults. Okay. The question is, if you only want an effective 10% slowdown in the performance of the process, okay, how many page faults, how frequently can the page faults be? Okay, so what we have said is disk is of this speed, memory is of this speed. This is a probability that we don't know yet. The question is, if you want a 10% slowdown of effective memory access time, how frequently can you fault? What's the probability of a page fault? The question clear? Show you how to do this. So if you say if it's a 10% slowdown, this is the effective memory access time. And this is the expression for the effective speed of access. We are saying this should be no more than 10% worse than directly accessing memory. So we are going to plug this with 1.1 M. Okay, that's a 10% slowdown. M is the speed of memory. 1.1 M says that's a 10% slowdown of memory access speed. Okay, so this is a number, this is a constant. This is also a constant, 25 milliseconds, which is okay. Now this, so what this is obviously okay, that's a straightforward equation you can solve for P. P is the only unknown. Okay, and you will see that P is actually, I don't know if it's in the next slide. If you solve this, you will see that page fault rates has to be one instruction every million instructions. Okay, in other words, this is 0.000001. That's the number you will get if you solve this equation. Okay. So page fault probability is that low. That says 1 instruction in a million should actually see a page fault. Every million instruction you can get away with one page fault, and if you have only 1 in a million instruction faulting, that will effectively slow down the performance of your process by no more than 10%. Any more page faults than that, you will start seeing much worse behavior. Okay? So what this should tell you is page faults have to be extremely rare events. Even a 10% slowdown, which is not much at all, okay, says that you can only afford to have fault once every million instructions. So you better have good locality. Once you fault and you bring the page in, you better not have page faults for another million instructions on an average. Yeah, because that's simply because disks are very slow. Okay, this is effectively about 1,000,000 times slower. So you need to have a 10% slowdown. You should have this approximately once every million instructions. Okay, that's what it is trying to say. Okay, is that clear? So you have to make sure that you allocate enough pages to a process such that it is not going to fault frequently. And in particular, if you bound, typically you don't put this bound, but this is just an example. There, even a small 10% slowdown limits the number of page faults to be very rare events, which is once every million instructions. Okay, so that's what you will get out of this. Yeah, so that's the performance of demand paging. Now, luckily, we can get away with this because most processes are well behaved. They exhibit what is referred to locality of ref, which is once they access a page, they access it repeatedly in time as well as in space. If you access page I, there's very high probability you will access the page ahead and page before it. Okay? Think of an array that's laid out in RAM contiguously. If you are accessing the ith entry, there's some chance that a loop may go ahead and access some entries down, and that's the next page that falls in the next page or some entries before. That's called spatial locality. Or if you access this page, you will access it again. You may fetch the next instruction from the page. Okay? Because of this notion of locality of reference, although this sounds like 1 in a million kind of event, sounds like very hard to do, most processes actually exhibit that kind of behavior because that's how most code actually behaves. Typically, you don't write random code where you go and say, let me access some part, I'm going to then jump to some random instruction, execute this, jump somewhere else. You will have sequentially executing processes with well-defined loops, functions and methods and so on. Because of all of this and data structures that are arrays or linked lists that you actually access in some reasonable way. Because of all of this, you get good behaved process behavior which exhibits high locality of reference, and you will see that because of good locality of reference, page faults will be rare if you do a reasonable job of allocating pages to processes. Okay, so with that we will stop here. We ran out of time. We're going to stop here today. We'll continue this discussion, talk about page replacement and so on next time.